Okay, so we're kind of taking a detour now. So we're done with, for the most part, ordinary differential equations. We're going to start something called boundary value problems. So instead of initial value problems, we're going to be doing boundary value problems. This first section kind of ties that with what we've been doing, but then we will move forward into partial differential equations in a matter of a few days. So this is 2-point boundary value problems. We've already kind of talked about this a little bit earlier in the year. But primarily, what we've been doing is this. I guess I should say so far, we've mostly been doing problems like this. Second order equation, whoop, that's not a derivative, sorry. So y double prime plus py prime plus qy equals 0, or maybe f of x. Okay, and then we have initial conditions going, such as y of a point equals y naught, and then y prime at that same point equals some other y value, which we'll call y naught prime. Okay, so now, and this is an IVP right here. So that's what we've been dealing with for the most part so far. Okay, first order, second order, maybe third order equations, not too many of those. And then you're given initial conditions both for a single point, both with y and y prime. Okay, well now our focus changes over to the same kind of equation to start with. But now we have boundary conditions. So y of some value alpha equals some y value, we'll call it y naught. I actually like this notation better. And then y of a different y value, let's say beta, or a different x value, equals some other y value, y1. Okay, and so the goal here was to find a solution, y equals, we'll call it phi of x, such that the graph goes through these points, alpha y naught, and then beta y1. Okay? And so what we looked at before, I don't know if you guys remember, but so a few units back, we did a problem like this, where we had a sine graph. And these were all potential solutions. Okay. And depending on what conditions you're given, okay, one of these three, or one of the many that we have, right, will be the one that goes through the boundary conditions. So for example, if I say this is alpha y naught right here, and let's say right here we have beta y1, okay, then we know that this larger one with the bigger amplitude is the one that solves that system, or that differential equation. Okay, so I mean it's similar to what we've been doing. Okay, but now the key here is, you guys, that different inputs are going to be provided. So instead of being given one single x value and working with that, now you have different x values potentially for y, maybe even y prime or a combination of that. Okay. So here's an example. So let's say we want to solve the boundary value problem, y double prime plus 2y equals 0. And we're given that y of 0 is 1 and y of pi is 0. Okay, you should be able to tell me the solution. I'm going to give you a few seconds here. So ignoring the boundary conditions, what's the solution for this? Root 2 t, or we're going to use x since we've been using x so far. Okay. Okay. I hope that's still in there somewhere.
Where is this?
Now, if you're struggling with Unit 5, then that's, I mean, this is... Okay. Now, let's continue. So since we have that y of 0 must be 1, let's plug 0 into this equation. If I plug 0 into this equation, we get c1 plus 0, right? Sine of 0 is going to be 0. So this means that c1 has to be 1. Now, if I do y of pi, that has to be 0. And now that's going to be c1 cosine of root 2 times pi. You sure?
So I forgot about the root 2, so that should be negative.
Oh, yeah, you thought -1. Yeah, the root 2 in there is why we have to kind of keep it like that. So here's what I have for the second equation. Now, we already know that c1 is 1, right? So you can pretty much ignore this, since that equals 1 anyway. And how do I get c2? Well, c2, I just move the sine over, or I'm sorry, move the cosine over and divide by the sine term. So that's going to be negative cosine root 2 pi over sine of root 2 pi. In other words, if we clean it up, that's the same as minus cotangent, bless you, of root 2 pi. So the solution, sorry, I'm trying to squeeze it on this one page. If I plug in the values now, that's going to be y equal to 1 cosine of root 2x minus, so I'm plugging in c2, that's cotangent of root 2 pi, and that's times sine of root 2 pi, or root 2x. Okay? Any questions on that? Okay, so slightly different approach with a boundary value problem, because you may not need, with all the other ones we've been doing y prime, plugging in, finding the derivative, and then finding the constants that way. So here it's kind of a little different depending on what's given to you. Okay, why don't you guys try this one? y double prime plus y equals 0. And we know y of 0 is 1, and y of pi is going to be, let's go with a constant a, any constant. All right, let me start going through. What's the general solution?
Y equals C1 cosine X plus C2 sin X.
Starting to remember, huh? Yes. Okay, so plug in the conditions. Y of 0 equals 1. That means C1 has to be 1, right? Now I plug in pi. That has to be a. So if I do that, I get cosine of pi. I know the C1 is still part, but since I've already figured out C1 is 1, I'm just leaving it like that, okay? Plus C2 sine of pi. Well, what happens over here?
0.
So this is going to be 0, which means that C2 can be arbitrary, but right here, this needs to be true in order for this to actually work out. Does that make sense? So I can't have A be anything. What does A have to be? What's the cosine of pi? Okay, so this equation would only be true or work, be valid, if A was negative 1. Okay, so only if A equals negative 1, the solution is going to be y equals cosine of x plus C2 sine x, where C2 can be any number. Otherwise, we don't have a solution. So if A were something else besides negative 1, this wouldn't make any sense because you'd get down to cosine of pi equals 2, let's say. Well, that's not possible. Okay? Does that make sense? I'm trying to go through like different scenarios that might come up here when you're doing BVPs because it's not like IVPs where there's always going to be one unique solution. Okay, here we might have one unique one. We might have a few different possibilities. We might have no possibilities. It all just depends. Okay. Let's try this one. Y double prime plus 2y equals 0. So same as the first one, but just slightly different conditions given. So let's say y of 0 is 0 and y of pi is also 0. Do we have a solution? In fact, that's the only one that works in this case. Is everybody on the same page? Okay, so we're back to the C1 cosine root 2x plus C2 sine root 2x solution. If you plug 0 in, right, y of 0 equals 0, plug 0 in, you get C1 has to be 0. You plug in pi, that has to be 0. Plug in pi, and now, since C1 is already 0, this term's pretty much gone. And then now we get that C2 sine of root 2 times pi has to be 0. Well, sine of root 2 times pi is definitely not 0, right? So that means that C2 has to be 0 too. Does that make sense? And so if both constants are 0, then the trivial solution y equals 0 is the only one that works in this case. We say it's trivial because it's a constant. It's not, a cosine and sine equation. It's just y equals 0. Okay. Last example, and then we'll kind of formalize everything a little bit. So try this one, same as the second one, with again slightly different conditions. So y prime plus y equals 0, and the boundary conditions are y of 0 is 0 and y of pi is 0. All right, what's the solution here? Y equals C2 sine of x. Very good. So when you plug in the conditions, we get any family of sine of x functions as a solution, right? So here there's actually infinitely many. Okay? So we've gone through a whole bunch of different scenarios. One problem where we had one solution, one problem where we had infinitely many solutions only if certain conditions were given, and then one where we had a trivial solution, and then one where we had infinitely many. Okay? Are there any questions on that? Okay, so what we're going to be interested in, you guys, before we start solving these, we want to know, getting into this, how we can tell whether there's going to be trivial solutions or not, okay? And so here's how we can do that. Okay. So we're going to introduce something called eigenvalues, which you may have heard of already, okay? Similar language, similar, and it's because of the number of solutions that we obtain and all that. But the eigenvalues here, so consider the boundary value problem y double prime plus lambda y equals 0 with boundary conditions given. Okay. So now, and you know what? Let's go ahead and define those. So let's go y of 0 is 0 again, and y of pi equals 0. So this is what we're studying, this particular example for now. Okay, and the eigenvalues are going to be the values of lambda for which non-trivial solutions occur. Okay? And now what we call, this is kind of a new one. Now we have something, or we're going to introduce something called eigenfunctions. Okay? The eigenfunctions are the non-trivial solutions associated with the eigenvalues. Okay, so for the previous two examples, so if we look at the previous two, we had two different lambda values. What were they? Okay, so when we had 2, would 2 be considered an eigenvalue?
No.
Why not? Right. So we had trivial solutions here. So not an eigenvalue. Lambda equals 1, though, gave us non-trivial solutions. So here, this is an eigenvalue, and the eigenfunctions were y equals c2 sine of x. Okay? Any questions on that? Okay. So here we go. So let's kind of just get down to business here. So same boundary value problem. Now let's actually explore how we can determine what the eigenvalues might be and when there's going to be, what the solutions are going to look like. Okay. So what we're going to do, first of all, just for the simplification process to make it a little easier, when we saw a 2 in there, you know how we got radicals as part of the solution and all that? So first thing we're going to do is we're going to let lambda equal mu squared, just so that when we start writing things out generally, we can avoid having to write a square root over and over, okay? And so now we have y double prime plus mu squared y equals 0. So then the solution would be y equals c1 cosine of mu x plus c2 sine of mu x. Do we know where we're getting that from? Okay, and maybe it's worth writing down at least one time. So remember that the auxiliary equation here is m squared plus mu squared equals 0. When you solve, you get m equals minus u squared. M squared equals minus mu squared. So then m is going to be equal to plus or minus mu I. So that's where we're getting these solutions from. Okay. Well, by the way, the fact that I just did this, I forgot to write this down, and this is very important actually. So this is the first of 3 cases. I'm assuming here that lambda is positive, right? So I'm assuming up here that we have, something greater than 0. 1, 2, 3, 4, 5. Otherwise, what I'm talked about doesn't make sense. We wouldn't get a cosine. We wouldn't get the solution otherwise. Okay? But now let's go through and figure out, with this case, if lambda is greater than 0, what transpires. So plugging in the conditions, remember y of 0 had to be 0. So if I do that, plug in 0 into this solution, you get that C1 times the cosine of 0, which is 1, and then the sine of 0 is 0, so I get C1 has to be 0. Okay. Now, if I plug in y of pi, that also has to be 0. And now, I'll just write it out. We have C1 cosine of mu pi, but since C1 is 0, this term disappears anyway. And then we have the second term, C2 sine of mu pi. Okay? So now what does that mean? Well, that means that C2 sine of mu pi has to equal 0. Remember, the goal for this was to have non-trivial solutions, right? So that rules out, if this equation has to be 0, that means, because we want non-trivial answers, right? That means C2 has to be non-zero. Does that make sense? Yeah. So that means that C2 must not equal 0. And so now, from here, we can figure out what values of mu would work. So what does that tell us? So what values of mu would make this equation equal to 0?
0, 1.
Mu can't be 0, because by definition we have lambda positive, right? So, but you have the right idea. What's the first value that works? 1, 2 pi, 3, all the multiples of pi besides 0 pi, right? So now let's go one step further, go back to what lambda has to be. What are the values for lambda then? 1, 4, 9, and so on, right? So, from here, so all of this implies that lambda sub n, the eigenvalues are just n squared, okay, for n equals 1, 2, and so on. And so these are the eigenvalues. And the eigenfunctions, new page, I don't think I'll squeeze that in there. So the eigenfunctions are going to be y1 equals sine of x, y2 is going to be sine 2x, and so on. So basically y sub n is going to be sine of nx for n equals, 1, 2, 3, and so on. It's just plugging in all those values that we figured out. Okay? Any questions on that? Okay, second case. Let's try to go through this a little quicker so that we can have a few minutes left. Let's go lambda is less than 0. So now we have y double prime plus lambda y equals 0 again. And so what we're going to do is we still want to introduce squares, just like before, so we can avoid radicals. But now what we're going to do is just put a negative attached to it. So we're going to let minus mu squared equal lambda. So then rewrite the equation. Whoops, I already screwed that up. That should be y double prime minus mu squared y equals 0. What's the solution here? Plus or minus mu, so then how do I translate that to our y equals equation? Good. Plus C2 e to the minus mu x. Good. Now there's actually another way to write this solution with hyperbolic sine and hyperbolic cosine. I'll define those later because you'll see that in some of the solutions they'll have that. So for now I don't think we need to worry about it, but let's just work with this. Okay, so plugging in what we know y of 0 is 0. So plug that in. We're going to get C1 e to the 0, which is just 1. I'll just write it out. Plus C2 e to the 0. And then if I plug in pi, that also has to equal 0. But now I get C1 e to the mu pi plus C2 e to the negative mu pi. So let me just rewrite this a little cleaner. So C1 plus C2 has to be 0. And C1 e to the mu pi plus C2 e to the minus mu pi has to also be 0. Well, let's see if we can solve it. When we normally have a system of equations like this, we try to eliminate or substitute, right? So what I'm going to do is multiply some here now by first equation. I'm going to multiply by minus e to the mu pi. So then, do you guys see that would cancel out what if I do that? The C1s would cancel out when I add, right? And now I'm just left with, let's C2. Well, it's really minus C2 e to the mu pi, and then plus C2 e to the negative mu pi equals 0. Again, our goal was to find what C1 and C2 are going to be, right? So we could factor out C2. And when I factor out C2, I'm going to just switch the order here. I'm going to put e to the minus mu pi first, minus e to the mu pi. And that has to equal 0. Okay. So now we got to kind of explore what this means, okay? So if we want non-trivial solutions, we want C1 and C2. We don't want them to be 0. So let's work with that assumption, okay? So that means we're going to try to figure out what mu is by setting that equal to 0. Okay, so if I set that equal to 0, move some things around. If we're trying to solve for mu, you could exponentiate both sides, or you can just see right here that these exponents need to be equal to each other, right? So this means what? How is this going to be true? Yeah, the only value we get here is mu equals 0, but lambda was what? Lambda was less than 0, which means that this is not possible. Mu cannot be 0 either. So what does that force our hands here? What does that have to mean? That means that C2 has to be 0. Okay? And similarly, C1 has to be 0. Okay? So the only solution is y equals 0, which is trivial. Okay, so that's case 2. Case 3 is a lot quicker, I promise. Okay? Case 3, what's the last case? Lambda equals 0. Okay? So if lambda equals 0, now we have y double prime equal to 0. We can solve this straight up real easily. What's the first thing I can do? It's a good thing we're reviewing this. What happens if I integrate? Y prime equals c. What do I do next? So let's call this C1 because we're going to bring in two constants, right? Integrate again. Now you get y equals what? There we go. And I'll save us the time. So using the boundary conditions, we get that C1 and C2 both have to be 0 again, which means only solution is y equals 0. Okay? So therefore, here's the conclusion. The only eigenvalues are the very first ones that we did, case 1, which were right here. Okay, so the only eigenvalues we have, I'm just going to rewrite it down here, are lambda sub n equals n squared. For n, a positive integer. This is just a fancy way of saying n equals 1, 2, 3. And the eigenfunctions are proportional, because we can play with that constant, but to sine of x, sine of nx. Okay? No other proportional to sine of nx. So we have sine of nx as the eigenfunctions and n squared were the eigenvalues. Okay? All right, so that's it for 10.1.